In this lesson, we're going to be covering rational functions. So to start off, right, what is a rational function? Up to this point, we have already covered polynomials. So a rational function is when you have two polynomials expressed as a ratio. So it's kind of just like one big fraction. We're going to go ahead and start off by actually finding the domain of a rational function. This is always going to be the same procedure when I ask you for the domain. So to find the domain of a rational function, all we're going to have to do is just set the denominator of the rational equal to 0. So just remember, that's the main thing. Every time you see find the domain and it's something that looks like a fraction, it's always going to come from the denominator. So let's go ahead and try an example here, right? So here we're giving a rational function. Again, this is what rational functions look like. They're just like big fractions. In order to find the domain, remember what we said on the last slide, all we have to do is just set the denominator equal to 0. So I'm going to go ahead and set the denominator equal to 0. I really don't care at all what's up here. We just focus on the bottom. In order to solve this, I'm going to have to move the 24 to the other side. So it becomes a positive 24, and then I divide by 4, and I get x equals 6. Now, this is why domains are important. If you plug in a 6 here, you're going to have 4 times 6 gives you 24, and then 24 minus 24 gives you 0. In your calculator, you could try out what is 36 divided by 0. Your calculator should tell you error. That's why domain is very important, because domain tells you what numbers we cannot use in the function because we're going to get an error or or something that cannot be defined or undefined. So this is the way you're going to correctly write the answer. You can write it like this: x cannot be 6, right? Because we already talked about it. That's the value that's going to be excluded. Or in this problem, they ask us for the answer in interval notation. So all you have to do is just think about it like this. So let me go ahead and draw this sign. We can use all the numbers in the world except 6. That's the only number we cannot use. So what numbers can we use? We could use any number here. So that's why we get from negative infinity to 6. And then we could use any number after that, 6 to infinity. Okay, so that one's just a little small example just so you can know how we can convert this into interval notation. All right, let's go ahead and try another example here. So again, state the domain of the function in interval notation. Again, we don't care about the numerator at all. We just grab the denominator and set it equal to 0. So that's always going to be step number 1. To find the domain, just focus on the denominator. Now, this problem is a little more complex, right? Because we cannot solve this problem by moving things around because there's two x's. We're going to have to factor this out. So again, we are already experts on factoring. This becomes x plus 9 and x plus 5. Again, if you have no idea how I got that, remember to factor a trinomial, you find two numbers that multiply to 45 and they add to 14. So that's 9 and 5. Of course, when we factor a trinomial, we have to divide both numbers by the number in the front. But in this case, the number in the front is a 1. So I could skip that step because if I divide by 1, nothing happens. Now, again, we already know how to do this. When you have two factors equal to 0, in order to solve this, you have to set each individual factor equal to 0, so each parentheses. So I'm going to go ahead and start by setting the first one, x plus 9 equal to 0, and then we set the bottom one, the second one, x plus 5 equal to 0, and then we solve. So I move the 9 over, becomes negative. I move the 5 over, it also becomes negative. So there you go. Those are my two answers, negative 9 and negative 5. Of course, when we're talking about domain, we write it like this: x cannot be negative 9 and x cannot be negative 5. Okay, so that's actually our domain. But since they're asking it for an interval notation, we are going to have to write it in a number line. So again, make sure you put them in order. The negative 9 comes first, and then the negative 5. So if they want the answer in interval notation, we know we got this. It's not that bad. It could be any number from here to here. So negative infinity to negative 9, not including the 9. Remember, the 9, we cannot use it, the negative 9. Now, the next possible answers could be all these numbers between negative 9 and negative 5, so hence this interval. And then, of course, negative 5, I cannot use it, but I could use any number after that, so negative 5 to infinity. Okay, so I don't want you to panic. These two things here, this and this, they mean exactly the same thing, but it just depends on the notation. So like I said, x cannot be negative 9 or negative 5, but if the problem asks you for interval notation, then you have to translate it and write it like this. Okay, And again, the reason we're excluding these two numbers is because if you substitute those numbers into the problem, you're going to get an undefined solution. All right, let's try again here one more, just so you can get the gist of it. Again, as soon as you see domain, who cares about what's up here? I don't care. I just care about the denominator. So I set the denominator equal to 0. Again, I factor this out like we already know. So two numbers that multiply to positive 32 and add to negative 12 is negative 8, negative 4. Again, I divide them by the number in the front, which is 1, so it doesn't do anything. Now, from here, you guys should know we're going to set each one of these parentheses equal to 0. If I solve the first one, the 8 moves to the other side, becoming a positive 8. This negative 4 jumps to the other side, becoming a positive 4. So x cannot be 4, and x cannot be 8, or in interval notation right here. Okay, if you have trouble converting this into interval notation, then yes, draw a number line. I'm not going to do it anymore, but you could do the number line if you think that it will help you out. All right, so that was enough for domain. Now we could also ask you to find the intercepts of a rational function, and this is going to be really helpful when we start graphing. So in intercepts, we know we could have y-intercepts and we could have x-intercepts. So this is the way we're going to figure them out. To find the y-intercept, we're simply going to substitute a 0 into all the x's. So just like we've done with polynomials in the past, every time you want to find a y-intercept, you just put zeros in all the x's and simplify. Now, to find the x-intercepts, we're going to set the numerator equal to 0 and solve. So if you saw previously, we get the domain from the denominator. But now that we're talking about x-intercepts, now I'm going to focus on the numerator. Now, this is a very important thing that we have to notice. You have to find the x-intercept after your equation or your function is simplified. Okay, and we are going to be talking about that during the next few problems. But again, you always have to make sure that your function is simplified before you find any x-intercepts. All right, let's go ahead and try an example here. So the problem, it's irrational. They're asking us to find the intercepts of the function below. So let's go ahead and start with the easy one. In order to find the y-intercept, remember all I have to do is just put zeros on the x's. So I have exactly the same problem, but I put 0 in the x on the numerator, and I put a 0 on the x in the denominator, and then I simplify. There's no such thing as negative 0, so I'm just left with negative 6. Same thing on the denominator, I'm just left with negative 2, and then negative 6 divided by negative 2 gives me the positive 3. Of course, this is not the proper notation, but I'll go ahead and put it at the bottom towards the end of the problem, but we already have our y-intercept. Now, if you look at the notes, to find the x-intercept, I have to make sure that this equation is simplified, but it's already as simplified as it could be, right? Because you cannot factor out anything from the top, you cannot factor out anything from the bottom. So no need to simplify. All I have to do is just set the numerator equal to 0. Remember, since we're talking about x-intercepts, now that's where we only look at the numerator. I don't care about the denominator. So negative x minus 6 equals 0. In order to solve this, I'm going to move the 6 to this side, making it a positive 6. And since an x is still negative, I have to make it positive. So the way I do that is I divide both sides by a negative 1, making my x into a positive and making my 6 into a negative. So there you go. That's my y-intercept. This is my x-intercept, but of course, they have to be written properly. So my y-intercept is 0, 3. There's always a 0 on the x. And then my x-intercept is negative 6, 0. And for x-intercepts, there's always a 0 on the y value. All right, let's go ahead and try a few more of these. Again, state the intercepts of the function below. This is a big function. So before we move on, I have to make sure that I factor this out in order to see if I could simplify it any further. So in order to simplify this, right, don't panic, but we already know how to do this. This is a trinomial on the numerator, so I have to find two numbers that multiply, in case you already forgot, to 8 times c, so 3 times 4 is 12. So two numbers that multiply to 12 and add to 7, that's 4 and 3. But then remember, you always divide those numbers by the number in the front. So I divide them by 3. 4 over 3 cannot be simplified, so I do bottoms up, where the numerator comes to the front, and I get 3x plus 4. And then 3 divided by 3 does simplify to 1. So this is how you simplify the numerator. Now we do the same thing in the denominator. This is a trinomial, so we do product and sum. Two numbers that multiply to 2 times 25, which is 50, and they add to negative 5. Those two numbers are -5 and -10. And again, every time you find the two numbers, then you go and divide by the number in the front. So I divide both of them by 2. 5 over 2 cannot be simplified, so I do bottoms up. The 2 comes to the front, giving me 2x minus 5. And then the -10 over 2 gives me -5. So the denominator is already factored out. Now, we had to do this because in some cases or in some problems, you're going to have a factor on the numerator that repeats in the denominator, and you would cancel them out. Okay? In this case, that wasn't necessary, right? None of these factors or none of these parentheses are the same, so there's no need to cancel out, but this step was still necessary because, like I said, in some scenarios, it is going to cancel out. So let's go ahead and move forward with what the factored form, because nothing cancels out, everything is still in there, but now I could proceed to actually find the intercepts. So in order to find the y-intercept, what I have to do is put a 0 in all the x's. So I put a 0 here, I put a 0 here, and a 0 on the both x's on the bottom. Just so you know, you could make a little note. Since nothing canceled out, you could actually substitute a 0 in the original equation. So you could substitute a 0 here if you like, okay? For some weird reason, I chose this one, so I put zeros there, but you get the same answer. So if I put zeros here, this cancels out. This is not needed because it's just 0. That's not needed. And the 2 times 0 is just 0. So I'm just left with 4 times 1 on the top, which gives me 4. And on the bottom, -5 times -5, which gives me a positive 25. This is a really weird y-intercept, but just leave it as is, right? It cannot be simplified any further, so that would be my y-intercept. Now for x-intercepts, again, look at your notes. A couple slides back, we saw that x-intercepts come from the numerator. So all I have to do is set the numerator equal to 0. So again, I don't care about the denominator. So in order to set this equal to 0 and to solve it, I have to set each individual parentheses equal to 0. So let's go ahead and start with the first one. 3x plus 4 equals 0. I throw the 4 to that side, making it into a negative. And then I divide both sides by 3, and that gives me -4/3 as my first x-intercept. Now, of course, I have to do the same thing with the second parenthesis. So I set the second parenthesis equal to 0. I throw the 1 to the other side, and it becomes negative. And there we go. Those are my two x-intercepts. Of course, we have to write them properly. So my y-intercept is 0, 4/25. And my x-intercepts, which I have 2 in this case, is going to be -1, 0 and -4/3, -4/3, 0. All right, not bad. Okay, let's go ahead and start making this a little more interesting. So up to now, we know how to find the domain, the y-intercept, and the x-intercept of rational functions. But we also have to learn how to find some little things called asymptotes, okay? Our rational functions are going to have asymptotes. Asymptotes are imaginary lines where the graph will approach. And there are 3 types of asymptotes we're going to be talking about. So the first one is what we call vertical asymptotes. Okay, so again, these are going to be imaginary lines on the graph. Vertical asymptotes go up and down, okay, and they are always expressed as x equals a number, okay? It's always going to be in that format. It's always going to be x equals. Now, the second type of asymptote we're going to be talking about are horizontal asymptotes. These go from left to right. Again, imaginary line, but this one is always written down as y equals a number. Okay, so vertical asymptotes and horizontal asymptotes always have to be equations. So it always has to be either x equals or y equals. Now, the third type of asymptotes, we're not going to be going much into it in this lesson, but I just wanted to throw it in here just so you know that they exist. The third one is what we call slant asymptotes. Another word for slant is oblique. And these are going to be written as y equals, and then you actually have an equation. So I just left it blank. You could have an x plus 1 and x minus 7. So you're going to have an x and then a number if you like. They could vary. That's why I left it blank. But these are the main 2 we're going to be focusing on in this lesson. So vertical asymptotes up and down, x equals. Horizontal asymptotes left and right, and they have to be expressed as y equals. All right, so now how in the world do I find these asymptotes? Good question. Let's start with vertical asymptotes. In order to find a vertical asymptote, you are going to have to set the denominator equal to 0. And I know what you're thinking. You're like, well, earlier you said that the domain comes from the denominator. Well, guess what? Vertical asymptotes do as well. But here's the deal. Vertical asymptotes come from the denominator of the simplified rational. So if you want to make a note of it, domain, which we learned earlier, comes from the original denominator. But vertical asymptotes will come from the denominator of the rational that's already simplified. All right. Now, there's another thing I'm going to throw at you, and I'm so sorry, but we're going to see this in an example right now. If you're in the process of simplifying your rational and something cancels out, then our graph is going to have a hole. And I know you're like, oh my goodness, what is a hole? Don't worry, we're going to do an example. We can visually see what a hole represents in a graph. But again, just make a note of it. A hole will happen or will exist when the graph of a function is simplified by dividing a common factor, or in other words, when something cancels out. So if we're factoring and something cancels out, we should make a note that that means the graph is going to have a hole. All right, so this takes care of vertical asymptotes. Now, how do I find horizontal asymptotes? That's what we're going to be talking about next. So in order to find a horizontal asymptote, we're going to have to compare the degrees of both the numerator and denominator. Okay, this one's going to be a little tough, so make sure you have good notes here. So when they ask us find the horizontal asymptote, first thing we're going to do is compare the degrees of the numerator and denominator. There's three different scenarios. If the degree of the numerator, which is the top, is less than the degree of the denominator, we automatically have a horizontal asymptote at y equals 0. Okay? So again, these are three different scenarios that you have to make sure you have written down because they're going to be very helpful, and it's going to be nice to have them handy for these types of problems. So the degree of the numerator is less than the degree of the denominator. I automatically have a horizontal asymptote at y equals 0. Super simple. Now the second scenario. What if the degrees are the same? So if the degree of the numerator is equal to the degree of the denominator, I'm going to have a horizontal asymptote at y equals a fraction. And that fraction is going to be composed of the leading coefficients of the numerator and the denominator. Okay, I know this looks scary. Don't worry. You're going to like these problems. They're not that bad. So again, if the degrees are the same or equal, I'm going to have to do a division of the leading coefficient of the top, the leading coefficient of the bottom, and then whatever I get, that's where my horizontal asymptote is going to be. All right, the third scenario is if the degree of the numerator is 1 or more than the degree of the denominator, then you don't have to worry at all. We do not have a horizontal asymptote. Okay, so these are the three scenarios. Again, to know what scenario we fall under, you have to compare the degrees of the numerator, denominator, see which one of these falls into it, and then that tells you what type of horizontal asymptote we're going to have. Okay, so let's go ahead and try some examples here. So look at this super tiny innocent problem. State the asymptotes of the function. So that means we have to find both of them, the vertical asymptote and the horizontal asymptote, and maybe even see if there's a hole in there. So first thing we have to do, remember, the rational has to be simplified. Nothing in the numerator can be factored out. Nothing in the denominator can be factored out. So this is already simplified. So it's ready to go. So look at your notes. How do I find a vertical asymptote? Vertical asymptotes come from the denominator. So all I have to do is set the denominator equal to 0 and then just solve it. So if I move the 2 over to this side, it becomes negative, and look at that, voila, we're done. That is your vertical asymptote. Okay, now for horizontal asymptote, this is the one that you actually have to think. For horizontal asymptote, let's go back to our notes. It has to fall under one of these three. Okay, so all we have to do is just compare the degrees. Let's go ahead and compare the degrees here. The degree of the top is the highest exponent on the x. But guess what? There's no x here. Since there's no x, our degree is 0. Now, the degree of the denominator. What's the highest exponent on the x? The x is right here. If there's no exponent, it's an imaginary 1. So the degree is 1. So what happens when the degree of the numerator is less than the degree of the denominator? So look at your notes, and I'll go ahead and go check real quickly. If the degree of the numerator is less than the degree of the denominator, we automatically have a horizontal asymptote at y equals 0. So wasn't that pretty simple? There you go. We have a horizontal asymptote at y equals 0 because the degree of the numerator is less than the degree of the denominator. And that's what the rule says. So that's it. There we go. We have found our vertical asymptote and we found our horizontal asymptote. And just so we have an idea of what it looks like, I went ahead and graphed this equation. And there you go. These are your asymptotes. So this is what they mean. It's an imaginary line, as you can see here at -2. This is a vertical one that we found right here. Because if you notice, the graph kind of wants to touch it, but it's never going to touch it. It's going to approach it. And then we have a horizontal asymptote at y equals 0. So it's right here. Y equals 0. Okay, so there we go. All right, let's try another one here. State the asymptotes. Again, both of the asymptotes. Before we do anything, we have to make sure that this is already simplified. So let me go ahead and factor this out. Because in the numerator, both of these numbers can be divided by 10. So I'm going to factor out a 10 because that's the greatest common factor. And I'm left with x, 2x, right? Because if I factor out a 10, I'm left with 2x plus 1. Right? So let me just go ahead and double check. 10 times 2 is 20x, and then 10 times 1 is 10. There you go. And then in the denominator, there's no greatest common factor. So that stays as 4x plus 1. And again, I had to do this to see if anything cancels out. So this parentheses would have to be the same as this if I wanted to cancel them, but they're not. So this is already in simplest form. Okay, so this is already simplified, but I did have to double check. So since it's already simplified, I could go ahead and find already my asymptotes. To find the vertical asymptote, we know that we just have to look at the denominator. So I'm going to grab this, set it equal to 0, and solve it. The way I solve it is I throw the 1 to that side, so it becomes a -1. And then I divide both sides by 4, giving me the -1/4. So that is my vertical asymptote. If it's a fraction, leave it as is, just simplify it as much as it could go. This one's already super simplified, so we're done. Now, to find horizontal asymptotes, we have to compare degrees. That's always going to be the rule. Horizontal asymptotes compare degrees. So degree, that's not a 0, that's meant to be a d, I'm sorry. The degree of the top, the highest x here, has an exponent of an invisible 1. And then the degree of the bottom, again, look at the x. What's the highest exponent? It's an invisible 1. So the degree on the top is 1, degree on the bottom is 1. Look at your notes. When the degrees are equal, we have to have y equals leading coefficient over leading coefficient. What that means is that you're going to grab the leading coefficient on the top, which is 20, and you're going to divide it by the leading coefficient on the bottom, which is 4. So what is 20 divided by 4? There you go. My horizontal asymptote is at y equals 5 because the degrees are the same, so we divided the leading coefficient. So again, that's what the rule says. When the degrees are the same, you divide the leading coefficient. So 20 divided by 4 gave me a pretty number of 5. And again, just as a note, horizontal asymptotes always have to be like this, y equals. Vertical asymptotes always have to start with x equals. And again, here we have our picture in case you wanted to see. We have our vertical asymptote at -1/4, which is like -0.25 right here. And then we have a horizontal asymptote at y equals 5. And there's our graph wanting to touch the asymptotes or approaching them. Next example. Again, state the asymptotes, all that good stuff. This problem on the numerator cannot be factored out. There's no greatest common factor. Denominator, no greatest common factor. Just make sure you note that we always have to check that first. So this one's already simplified. So to find my vertical asymptote, all I'm going to do is set the denominator equal to 0. If I set this equal to 0, I'm going to throw the 2 to this side, making it positive. But then we divide both sides by -1 because this x has to be positive. So the 2 which came over here and became positive, after I divide by -1, it changes back to negative. So that's how I got my -2. Now for horizontal asymptotes, again, we know the procedure. We have to compare degrees. Degree of the top is going to be an invisible 1. So 1. Degree at the bottom, again, an invisible 1. So what does the rule say? When the degrees are the same, I divide the leading coefficients. Leading coefficient is a number here, which is an invisible -1. And then on the bottom here, it's also an invisible -1. So what is -1 divided by -1? Gives me the +1. So there we go. My horizontal asymptote at y equals 1. Again, because the degrees are the same, so we divided the leading coefficients. And here is our graph. We have a vertical asymptote at -2, and we have our horizontal asymptote at 1. All right, we only have 2 more examples to go, so let's go ahead and try something a little more interesting. State the asymptotes of the function below. Again, you have to make sure that this is super simplified. So maybe it simplifies or maybe it doesn't, but we still have to check. So these are trinomials. So there's a 1 here. So to factor the numerator, I have to find 2 numbers that multiply to 1 times -14, which is -14, and they add to -5. So those 2 numbers are -7 and +2. Now, denominator is also a trinomial. So let me go ahead and put a 1 here. 2 numbers that multiply to 1 times -12, which is -12, and add to -4. Those 2 numbers are -6 and +2. Now, the reason you have to factor out is because, like I told you earlier, sometimes things cancel out. Which, if you notice, is the case in this problem. We have an x plus 2 on the top and an x plus 2 on the bottom. So those cancel out, leaving me with a simplified version of x minus 7 over x minus 6. Now, this is where things get interesting because if you remember the notes from a couple slides back, when something cancels out is when we have a hole in the graph. So every time you cancel out, go ahead and put a little h here, just so you can remind yourself that your graph is going to have a hole. Okay? If 2 different things would have canceled out, that means the graph would have 2 holes. But in this case, just 1 factor canceled out. So what we're going to do now is we're going to have to set whatever canceled out equal to 0. So x plus 2 equals to 0. I solved that by moving the 2 to the other side. And that means that the graph is going to have a hole at x equals -2. All right, I know you're anxious to know what a hole looks like in a graph, so just give me a minute. I'll show you the graph right now. But let's go ahead and continue finishing the problem. So again, that cancels out, meaning there's a hole. You set that equal to 0, you get your answer. Now we proceed to find the vertical and the horizontal asymptotes. But remember, now we're going to be using the simplified rational. Okay, so if you remember on your notes, to find the vertical asymptote, you have to use the simplified rational. So vertical asymptotes come from the denominator, so all I have to do is set the denominator equal to 0. So x minus 6, set it equal to 0. I throw the 6 to the other side, giving me a +6. So again, if you would have used the original denominator, you would have used 2 answers, and you would have had 2 answers, and one of them would be incorrect. Because remember, you have to use the simplified rational. So we only get one answer, the x minus 6, which becomes x equals 6. Now, to find our horizontal asymptote, it's always the same thing. You compare degrees. And here's the fun part. You can use either this one or the new one. You're going to get the same answer. So let's go ahead and try this one just for fun. Again, horizontal asymptotes make us compare the degrees. Degree of the numerator is 2. That's the highest exponent. Degree of the denominator is also a 2. So the rule says that when the degrees are the same, we divide the leading coefficients. The number in the front here is 1, an invisible 1 as well. So 1 divided by 1 gives me my horizontal asymptote of 1. Y equals 1. So again, the biggest thing here, my biggest worry is that we forget, right? Remember, once you simplify, that's the one you use now. And when you cancel something out, it represents a hole on the graph. So here we go. Here comes the fun part where we actually see what a hole looks like in the graph. So let's go ahead and start by this one. Our vertical asymptote, we found it to be at 6, which is right here. We found the horizontal asymptote to be at y equals 1, so right here. And then wherever the graph is at -2, we draw a little hole. So the graph at -2 is right here, and it's represented by a little empty circle there. So you draw the graph normal, but then you erase that and just put a little open circle. Okay, and again, if you want to know what a hole means, it's kind of like a domain, right? The graph doesn't exist there. Because again, if I were to plug in a -2, and you could try plug in -2 into the problem, and you're going to get an undefined solution. So that's why it represents, it's represented by a hole. All right, that was pretty fun. If you were confused about this one, again, just make sure to let me know and we could do another similar example. All right, this is the last example from this video. So find the asymptotes. Again, we have this problem, and just like any other problem, you always have to factor it out first. So I cheated. I factored this out because we already did it early on in the video. So if you look at the notes from this video, you'll see that we had already factored this out. So I just copy pasted it here. So this is already factored out. Obviously, nothing cancels out. So that means we're not going to have any holes on this graph. But this is really going to help us find our vertical asymptotes. So to find our vertical asymptotes, again, we just look at the denominator. So I'm going to set this parentheses equal to 0. So 2x minus 5 equal to 0. I throw the 5 to this side, making it a positive 5. And then I divide both sides by 2, giving me x equals 5 over 2. And then, of course, I also have to set the other parentheses equal to 0. So x minus 5 equals 0. I throw the 5 to that side, giving me a positive 5. So I have two vertical asymptotes in this problem, and that's perfectly fine. This one of them would be the left one, and one of them will be the right one, and we'll figure that out right now. But again, it's just in order from least to greatest. So that's my vertical asymptotes. Again, we don't even care about the numerator. Vertical asymptotes just come from the denominator. If you're asking yourself, why did we even have to factor it out? Remember, we always have to do that because sometimes things canceled out like they did on the last problem. In this one, nothing canceled out, but we still had to factor because that makes it so much easier to just set each factor equal to 0. Now, for horizontal asymptotes, we know the drill. I'm not going to do the D for degree anymore. I'm just going to go ahead and circle them. The degree here is 2. Degree of the denominator is also 2, so we know the drill. The notes say that when the degrees are equal, we divide the leading coefficients. So the leading coefficient here is 3. Leading coefficient of the denominator is 2. So 3 divided by 2 is not a whole number, so we just leave it as a fraction. So my horizontal asymptote is at y equals 3 over 2 because the degrees are the same. So we divide the leading coefficients. And here is a graph in case you were wondering, right? So we have a horizontal asymptote at 3 over 2. And then we have a vertical asymptote at 5 over 2 and at 5. All right. Now, of course, again, like I said, one of them is your left and one of them is your right. You just put them in order. So this one would be your left vertical asymptote and this one would be your right vertical asymptote. Okay, so you don't have to label them, but just in case on the homework they do ask you for which one's the left, which is the right, that's what you would do. You just put them in order. Obviously, the smallest one goes on the left and the biggest one goes on the right. So I know this was a lot of information. If you do need more examples or clarification, just make sure to reach out to me.